Good morning, good afternoon, good evening from whichever the part of the world you are in. So today we have with us Dr. David. He's an expert structural engineering geologist, and he specializes in characterization of ground condition for significant infrastructures in Sydney area. Dr. O's impacts contribution extend to high levels scrutiny of projects, and he plays a pivotal role in strategically planned transportation tunnels beneath Sydney Harbour and was instrumental in recent strategic planning, such as Faster Rail program. He is also an academician. He in his academic pursuits he explores faults and dike systems in Sydney region, conducting structural analysis and age dating. So we are very happy to have you on our webinar platform,
Yep.
Dr. David. So it's up to you. It's the screen is all yours now.
Oh, thank you. Welcome everybody. As you can see, the presentation is on Sydney Metro, City and Southwest. Basically exposing more geological unknowns. It was pretty much unknown what we encountered during these projects. So I hope you enjoy. Let me just press this. Whoops. Okay.
Yeah, I'll just let you know if something is wrong, and I'll
Yep.
be switching off. I'll be switching off my camera for now.
Yep. Okay. Just a brief contents. So I'll provide an overview of the project or projects now. Sydney Harbour tunnelling history. What we do is you start off with a desktop study. So we're looking to find gaps in data or information. Once we have that, we plan up the geotech investigations. And this also allows us to define alignments based on geology. And from there, once we have the investigations, we're able to characterize. And once we have some insight into characterization, then the vertical alignments are adapted. Tunnel boring machine selected. And what I'll do is just highlight some of the construction and a few conclusions. So the picture on the right is a borehole we did right during tender stage, and that's just a floating barge with a sonic drill rig on probably one of the highest frequented harbours in the world, and probably the most beautiful. This one borehole cost us $80,000, but during tender, this one borehole saved us the taxpayer a lot of money. And you can see some of the work that was done, having vertical alignments, boreholes, and characterizing the Pleistocene sediments and the Holocene sediments across the thing. So what we have, Sydney, is a new metro system. A lot of this began back in 2008, but it was stopped because of political reasons. But from 2014, 2010 it began, and we had the Northwest Metro, which is now operating. So that's from Chatswood through to Tallawong, so the northwest side. And it did repurpose an old rail line from Epping through to Chatswood. So it was new construction and then repurposing old. The project I'm talking about today is the blue line. So this is from Chatswood through to Sydenham. So that's 15.5 kilometre tunnels, and then repurposing an old grade alignment all the way to Bankstown, and that's where I'm presenting from. So that's where I live. So Bankstown was named after Sir Joseph Banks, the famous botanist. And so there's a bit of history here. To the west we have the new metro that connects the Metro West to the main West line here. And in recent times, the other project I work on was the Metro West, which is this teal line, and from Westmead, where's a central precinct of hospitals there, through to Parramatta, and all the way to where they held the Olympics in 2000, and into the city where, in the CBD, that's where they're constructing a massive cavern underneath the city of Sydney, close to the old Martin Place. So the Sydney Metro, City and Southwest, basically, to make this happen, we had to address the key issue, that was the harbour crossing. We've had harbour crossings before. To the east, we had an immersed tube that was laid down in the 1990s, but this would be the first project that would go basically sub sediment underwater. So the 30-kilometre extension of the metro from the northwest line, as I presented, through to Sydenham out here is something to take Sydney into a new way, because the old lines are starting to get congested, and this one here is to allow new developments and a lot of suburbs in the northwest, but also in the southwest and west. So as I explained, the tunnel was a 15.5 kilometre segmentally lined tunnel. So the tunnels are fully tanked. They're and and as I explained before, the Metro West is 24 kilometre, and the Metro West is Western Sydney is 9.8 kilometres. So there's a lot of mine cross passages. The cross passages will have sumps, substations, and diving portals on each end. You can see the work we did was on top a jack-up barge on Sydney Harbour, so you can see how congested it gets on these sort of projects. So just a bit of history of tunnelling in Sydney. Really, the first tunnel we could call is a coal mine. Um, so the history about the coal mine was, we had a famous geologist, Edgeworth David, who put his career on the line to actually drill a borehole until they intersected coal, and that was at 895. But it wasn't in this location. It was on the northern side of Sydney, a place called Cremorne. But as they wanted to produce coal to generate power, the residents in that area didn't want it. So what they did was they put it to the poorer side of Sydney at the time, but this is probably the richer side of Sydney here now. And so in 1897, they sank a shaft to 895 metres. And as you can see here, the shaft is fully brick lined all the way down. And the actual coal seam is the bulleye seam, which sits at the at 200. It sits in the Permian coal measures, where the rocks that we see in Sydney are Triassic. So you can see how they produced a heading that sort of went east, and they actually mined underneath the harbour area of Sydney, and you can see the old Scottish people here coming over and working in these really tight, cramped areas, board and pillar type, just sort of columns and pillars and that sort of stuff. And you can see here an old rail line, and that's down at 900 metres below Sydney Harbour. But over time, this area was subject to a lot of um, roof collapse. There's a high horizontal stress that's locked in, and so we had floor heave, roof collapse, and high heat was recorded in these areas here. And this also had the issue of methane. And in the late in the mid 1900s. It was actually closed because there was an explosion with methane, and these whole shafts were backfilled with fly ash and waste, and sealed up, and now it's a thriving suburb in Sydney. Probably another one that I presented is, at the moment, there will be another tunnel crossing across here. So this will be the Western Harbour Tunnel, and I'll probably show that in a slide down the track. So really the first mine tunnel under Sydney Harbour was the Sydney Harbour Cable Tunnel. So this was a transport project to actually get electrification from the south to the north, to allow the electrification of the railway lines to the north of Sydney. And so this was a drill and blast tunnel. And as you can see here, the history of it, they started in 1913, but by the time they got to 1915, they'd got to a point of the harbour, and with limited investigation, the harbour encountered a whole lot of mud and water at that heading. And so after 3 months of fixing up and grouting, they tried again, but they came into the same issue again. So they called it a fissure, but and I'll explain later why why it's not a fissure in this location. But 1916, they pulled back and closed up, and then went down deeper. And by 1918, they hit a major geological fracture. Well, and they had like up to 2,000 litres per minute. So this required a whole lot of grouting, and this was completed, I think, within a period of 3 months. And as they projected, they hit the same structure again as they were heading up, with 800 litres per minute. And by 1922, with one order of magnitude in cost, this project was finished. And now this tunnel is basically just closed and full of water, never to be reopened. So it's just a bit of history that the author down the bottom was able to pull together. So the IMT tunnel that I talked about, so you can see where the Opera House sits here. This is some bathymetry and LiDAR. So the bathymetry shows the rock armor on top of the immersed tube. But here you can see where the segments were being laid down. So this was a major project, was in the news during in the 1990s, and this was done by Kumagai Transfield operation across here. You can see here the vertical alignment, and you can see to the south you still have an area of Pleistocene sediment, usually just hard silty clays. But during the Holocene, at the end of the this was eroded out and then backfilled with sort of sands, and the sands became dense, but as you progress to the top, they sort of became loose, with a drape of very soft silty clays up the top. And here's a profile showing the construction method they adopted, and what they did was they tapped back into the Hawkesbury sandstone either side. So that was our first successful tunnel in Sydney Harbour. So what we undertake in here in Sydney is, or across Australia in these programs, is a desktop study. Basically, it pulls together a whole lot of geological, geotechnical, and just knowledge of what's happened in the area. So what we have here is the Sydney Basin, and it's a Permo-Triassic geological region, and where we sit in the central part of it. To the north, we have Permian coal measures, and the Permian coal measures that they mined are at about 900 metres below this central part of Sydney here where they mined. Minor deformation and warping in the basin from the late Triassic through the Paleogene contributed to the faults, formation of faults and joints and dikes. And these are the things that I've been studying with local universities. The major river systems have eroded along these structural weaknesses to form these really deep incised valleys through the uplift of eastern margin of eastern Australia. What we've got behind Sydney is the Great Dividing Range, and that's a product of it. Sea level rise in the Pleistocene resulted in the sediment infill of these valleys. And we did have some dates in these, which are up to 60,000 year old at the deepest. So it sort of just highlights the age of when this was all happening. Following this Pleistocene erosion, the Holocene sea level rise resulted in infilling of valleys with these Holocene sediments that are just very soft, and when you run geophysics on them, they basically have the same velocity contrast nearly as water. So they're interesting. And here you can see the work. This is some of the publications I've done, and just using GIS and geotechnical database to capture where all our knowledge is. So finding the gaps. So identifying dikes. There are a lot of geotechnical reports around. So to build up our models, the reports come through, and a lot of the times they're able to map these structures. So mapping them, you've got a property boundary that you can snap to, and then you can define where these things, and over time you build up a really good model along strike, and then you're able to infer between them. And also here you can see where they've actually drilled a borehole, and you're able to, we know where the borehole sits, the collar, and project the borehole in its inclined nature, and measure where that dike sits. And you can see here the information that's captured in the attributes for what's in these databases. So what we have on Sydney is an old geological map published in 1983, based on information from the 1950s, 60s, and through to the 70s. So it's really not it represents what we have, but it doesn't provide sort of really close definition of what we need for engineering. So, and some examples of past, interpretations of these deeply incised valleys across Sydney. Some of them based on boreholes, which are the little upsided triangle, the triangles here. So Iron Cove Bridge to the west of Sydney, Garden Island where the naval base is, Rosehill Bridge is to the north, and Warringah is another place up to the north. So so there's a lot of information that we can tap on, and that allows us to focus on our investigations. So what we did have was some old geophysics that was done in 1973. This work was planned, and there was a few iterations of studies done across here, and a whole lot of assessment was based, and the top of rock was based on what was highlighted in this geophysics. But we did note in some locations there were deeper spots of this geophysical information here, and from that we sort of indicated to the client that we really need to get in here and do some investigation if we plan to put a tunnel through this area. Yeah. So to the south of the project, we picked up, there was an old tunnel that was built in 1940s, and what this tunnel had was really detailed geological mapping along the tunnel as you went from west to east, and it was quite important because this here has allowed us to define where we've got geological structure along say from this point to this point here, which is from this shaft through to this shaft, and you can see the structures, the joints that were picked up around this. It was quite an amazing find to have this sort of information, and yeah, this really allowed us to develop the program a lot more. And again, another tunnel that was done just to the south of Sydney CBD, Redfern area. So this is just an electrical tunnel that was put across, but some of the major structures that are picked up, and yeah, you can see here an identified fault zone that we understood been coming through Sydney, but where that was, it picked up the major structural elements in that. So quite important to find all this historic information and capture it for the future. And again, another tunnel. So this was the tunnel that I noted here, and you can see the regional geology that had been mapped. And this is mapping I've been doing since 2006, even earlier, and we've been publishing this and doing age dates. But to find this extra information actually provide us a area where we know where we've got this geological stuff, you know, underground. And yeah, the city tunnel that I just showed here. So you can see where all the major structures were along those areas there, and the strikes within those tunnels seem to match up with the strikes externally that we've mapped. And so this is how we've built the model up, and also based on borehole encounters and that sort of information collected as we look subsurface. So yeah, using GIS in these programs is just so good to have that sort of validation from spatial information. What we do have over Sydney is an old air photo that was from 1943 that just sat in archives for a long time. And back in 2008, a colleague from New South Wales Roads came and showed me this while I was still at the Geological Survey, and this was just such a great production. And yeah, you can see here we're looking at old brick pits in the southern part of Sydney down here, and yeah, the definition, I mean, is just quite great. And even to the north at Artarmon, and we had another brick pit here. And yeah, this was quite important because in our design we were trying to lace a tunnel through this area. So yeah, and yeah, you can see here on an early part of the thing, we had a tunnel through this brick pit here. But when we looked into it a bit more, we noticed that when they built over it, they had major pile foundations. And so what we did was we aligned the tunnel, which was the work that I think we presented at RWTC this year. So it was trying to get this sort of you just use the road as a corridor rather than go underneath the old tip. And here again, hopefully you like air photos. Sorry about this, but as we go from left to right, you can see 1943 just gives you a history of what developments happened over time. And here we are planning in 2015, and this is the canvas that we have. But having these air photos just highlights what's around and our understanding, because this was a very industrial area, but also during 43 it was during the World War, during the war, and so we had to understand that we didn't have issues from military, military um, you know, um, things in this area. So yeah, these are things we overcome. Then you can see the amount of boreholes that were done in these areas, and yeah, this allowed us to understand where rock levels were. But what during our design, we also added on boreholes where we needed to get depth and understand stress regimes, groundwater regimes, and all those sort of things. So it was being close to a harbour. We want to understand tidal fluctuations as well. And then if we go back further, you can see maps from the earlier Arthur Phillips days. Same area, different maps. 1830 maps at 1922, and when you lay them all into a GIS, you just get this maze of how this whole part of Western Sydney CBD developed. But now it just in these locations here we have big high rises, and it's a really developed area from its old industrial heritage. So what we do with the GIS, you can see pulling everything together with boreholes, then being able to define geological structure, using old historic geophysics data helps us define bathymetry and also understand where top of rock is in these areas that we need to focus. But on top of that, it allows us to define where we're going to do our say a geophysics run, and that's what these sort of highlighted zones are here. You can see the bathymetry here, and what's interesting with part of the design is where you come around these heads, you do have these really deep zones, and you come around these sort of zones here, and you have these really big zones where the water scours out the sediment. You get big holes, and during the geophysics that we're doing, you can, they pointed out, well, there's a big shark down the bottom there. So it is full of life down there, and GIS just allows so much data to be captured and then transferred on as the program progresses. So once we did all that, we planned all our boreholes, and so from harbour boreholes, we had two jack-up barges on the harbour where we're actually drilling. Most of them we had success with in setting up, but in certain locations we couldn't set up because the spuds here couldn't, given us, couldn't set in properly. So there were failed attempts, and hence what I mentioned at the start. This one borehole here, we had to go back into a location where we couldn't set up with this. The other land-based ones, you can see Central Railway Station, which is a main connector for the whole Sydney rail network, and here we are drilling, 40-meter deep boreholes in an old where they used to park trains, and next to a moving thing. In this case here, we had a planned station that was going to be excavated in here, and it's actually open now, so it's all being constructed. There's a big station ready for the metro to happen, with a tunnel that crosses east to west on this, based on from our early days doing this drilling. So this drilling involved a lot of lab testing, but also in situ stress tests such as packet tests and stress testing. Then we did do inclined boreholes to target a major dike running through this area, and so to build up our model, but also characterize what we have there to go forward. So here's the work on the harbour. So the bathymetry, this allows us to understand how deep the water is. So we can actually plan where our barges are going to go. But also it actually gives an idea from the geophysics we did to the bathymetry, how deep our boreholes have to go to achieve what we need for the project. So yeah, this is sort of really detailed bathymetry, and yeah, it's quite deep there. So yeah. So the other thing that we undertake is geological mapping. So we undertook a series, a few days mapping around the northern shore of Sydney Harbour, trying to understand where these dikes go. Because the old map that I showed you earlier, these dikes that we mapped here are 150 metres north of where they were on the geological map. So we're just trying to get things right. And how we do find out where things are, well, on this northern side here, or this northwestern side, we have this brick wall, retaining wall, but it actually sat between really competent sandstone on both sides, which had jointing striking the same direction as this through here. So what's the retaining wall holding up? Something of weakness, and that most likely would be the dike. And on the southern side, on the southeastern side, we had the same issue again. We had highly fractured rock, but also a retaining wall holding something up here as we came across to this location here. And so it's sort of interesting to understand using um, retention systems put there over time, why they're there, and hence why highlighting this sort of provides an understanding to the designers later that there may be a dike. And in this case here, it's so populated that we just can't get in there to investigate. So we have to assume that there could be something there. But in the case of the dike down here, here's another retaining wall with jointing striking parallel to this system here. And so what we did undertake was some drilling across that feature, and we did highlight that there was a dike there. So yeah, so this basically here just highlights the aerial photography of the map and how built up it is in this area and where we want to put our tunnel. But looking at the geological map from '83, you can see that where the old dikes were and where we actually mapped them. And in the case here, we proved where it was. Okay, Sydney Harbour. Well, Sydney Harbour is a very, very trafficked harbour with containers, ferries, and cruise liners, and it's really hard to um, set up and drill. So we had to do it um, in the season where we didn't have cruise liners, and we were very mindful of when containers were coming in. So the containers come up the harbour around through here, and then they park up here. And you don't, when I looked at one coming in the other day when I crossed Sydney Harbour Bridge, and there's not much room there. And so all our investigations were targeted along this area here. And so a part of it was mindful of these really major constraints. Because if this was coming in, then we'd have to pull up everything and move to allow this to come through. So they have priority over everything. Ground investigations. So most of our utilities are all underground. So you can see here it's pretty well concreted up to buildings and paved in the city, and just pretty well paved, similar to all over the world. But what's interesting is when you look at what's under the ground, it's quite complex trying to put a borehole in these locations when you've got all your utility assets under the ground. And you've got your major. This is the planning of our complex tunnels below a location. You got tunnels. You got planned walkways and all that sort of thing. And the big issue we had was we had a borehole plan, but 12 o'clock at night, you get a phone call saying, well, we sort of they do non-destructive drilling down to 1.5 meters, but they couldn't go anymore because they found an old asset that we just didn't want to. So a lot of drilling was cancelled because of the issues of the utilities below the surface, and especially in a CBD, you hit one of them, you'll have a major issue on your hand. So geotechnical and geophysical investigations. So you can see here we did undertake a marine mag as well to assess for any steel or foreign bodies of metallic nature that were in the harbour, because we had a harbour bridge that was um, constructed. So we had no idea where the alignments were going to go at the time. And we had to understand what things were there metallically, but also we used it to try and define if there was any geological dikes, because they may transmit some magnetic response to the marine mag as well. So you can see here the amount of reflection surveys that we undertook across the harbour to get this high resolution information to provide us with that sort of understanding of where rock was. And here you can see the boreholes that we did through here. Um, so as I said before, we had 2 jack-up barges, 24 boreholes that we undertook, in situ stress testing, because we weren't sure if we were going to go deep into the rock or whether we ended up going into the sediment. Water pressure testing, sampling of sediment coring, CPTs, to allow us to characterize the sediments, um, sonic coring, as I showed at the earlier photo, and a whole geomechanical testing of the soils and rock, and also sedimentological analysis of these two for TBM selection. So the use of yeah, testing the sediments. We used, because some of this was very limited when we got our samplers. A lot of the sand would escape, so we did use one of the local universities and my old professor to test the sediments to provide us with sort of density contrasts and resistivity and all that, and allow us to produce some lithological understanding of these of the core that we're pulling out, the silty clays and that. In some of the older, this one here is 35 meters depth, but we're already in this location. We're really already in 17 meters of water, so that was 52 meters below the surface. And we did have a this old charcoal seam that we uncovered in this core cut, and so when we dated that, that sort of came back with a 63,000-year-old understanding. So this also helped us in profiling and, at the end of the day, characterising the sediments that we ended up tunnelling through. We did use some new techniques out of the Geological Survey of New South Wales, HiLogger. This provides an understanding of the mineralogy of material and also the clay contents, and the and other sulfate type mineral sort of stuff that we get. This has sort of allowed us to correspond this with just normal lab testing as well. So that borehole I told you about, this is the borehole here that we did on a major street heading down to the harbour. And so here, this is the one of the boreholes. Yeah, so this was quite significant, and it actually validated our geological mapping. So the land stuff, we had up to 197 boreholes across the whole alignment. average depth of 25 metres, some up to 60, 70 metres. CPTs in areas of soil, and a whole lot of test bits for contamination testing, especially around that central precinct, because we had old gasworks, but we also had cemetery where I showed that drilling next to the railway station. So we did all this investigation and we did not find anything that was related to a cemetery, but when they dug up, they found a cemetery. So, yep. So you can see here the Hawkesbury sandstone is really quartzose, spectacular sandstone. So if you come and visit Sydney, well, yeah, you will see the Hawkesbury sandstone. But yeah, cutting its way through it are these dikes, and the dikes can be high strength up to 160 MPa, but they can be highly weathered, as you can see described through here, where they're just hard clays. The other thing that defines the Hawkesbury sandstone are the joints that we get. A lot of them are related to tectonic events, faults, and that, as I showed you in those GIS maps above. So this is some of the work I did to complete up when we were finishing our reference design, was to have these 3D models, because we had to, when we were designing the tunnel crossing here, we'd selected to go through the sediments rather than go in the rock, because the rock had high water pressures, and we couldn't get the vertical or the vertical grade for the trains to get up to the stations that we had planned. So this was our opportunity. You can see the refraction survey here, highlighting sort of rock levels, but also picking up little anomalies that do show that these deep valleys here are produced by a major thrust event that's throwing the north up 50 metres from the south, so it's quite important. And here you can see where the reflection surveys have been readapted to correlate with the boreholes. Also, some of the things we uncover is, some of the fragments of the past, from shell fragments, worm tubes, through to microfossils such as ostracodes and those sort of things there, which help us understand where we had marine environments, where we had estuarine and those sort of things here. But as I pointed out, that anomaly, we did pay attention to that anomaly I showed before. And so what we did, we set up 2 jack-up barges on the harbour, 50 metres apart, and we undertook a borehole to borehole tomography survey, and this allowed us to understand the velocity contrast between the higher velocity rock here and the low velocity here, which corresponded to the borehole that we here, which is this low angle structure that we have here, and that just sits in this location here. So it sort of highlights that this major geological structure is happening through this here. You can see the use of CPTs was really good in characterising the sediments through this, and this gave us an understanding where we were going to put our tunnel, the 2 red lines. What we did uncover with one of the boreholes was a large boulder. So there was a colluvial deposit, and part of the large boulder that we uncovered in the borehole here, we shifted our tunnel just above that sort of line, and successfully it was constructed. And you can see, the ages between the sediments, 22,000 years, 23, and then up at the top we had 9,000-year-old sediments. So it's a long-lived time, that was in this time here. And so this is the final characterization of what we did from all those investigations. And you can see from the bottom, we had the colluvial material. We had the sediments that was sort of produced from river running down. And then we had the input of the Pleistocene silty clays. You could see the shells through that. The sediments below, we had no shells. And then the sand units and up to the Holocene here. So you can see the ages here on the left define the ages across here. So it's yeah, these are pretty deep valleys and pretty spectacular if you go out to places like the Blue Mountains, or even in Sydney if you go up to Lane Cove or down to the south, Sutherland, in those national parks there. They're quite spectacular. So yeah, this is the sort of 3D projection working with the tunnel designers to to get our alignments right. So it yeah, we fit within the in the constraints that the experts who are in the background designing these sort of um, um, these tunnels. So as we head from north to south, this is a very squeezed up alignment, but I just wanted to highlight the issue of the oops, go back, yeah, of the geology that has been raised um, from north up to where we've got it initially. Yeah, this sort of dips down, but there's another major structure. This sort of a line, this sort of curves to the east and then curves back to the west. So this section does highlight a lot of major structure, and this was there was a publication done back in WTC 2022, and the geologists who worked on this on that project there actually presented the structures that he uncovered in this location here. So it was quite good to see, our predictions being captured in road tunnels where they actually mine using road headers rather than us in TBMs with segmental lining. And you can see here it's very um, yeah, it's very vertically exaggerated, but it does show the difference between the north and the south of Sydney along that alignment. And that was the issue we had, was we had a station here at Victoria Cross, we had the station at Barangaroo, and the grades here getting up were limited at 4%, and so we were able to achieve that to get a station which is constructed, ready to go. So the marine investigation, the sediments, so the particle size distribution, the characterization of that. This allowed us to use these in understanding the different sediments we had, but also to later on define what TBM we were going to use. So so you can see a whole lot of X-ray diffraction to identify mineral phases, and then just plots to try and characterize the groupings of these materials. Also sort of the Atterbergs, and yeah, you can see the PSDs being used to characterize where we sit, where the tunnel sits. So so just with the characterization, probably you probably had enough of that, but unit 1 sort of defined by that loose sand, soft silty clays with shells. Unit 2 here sort of well sorted sands with silty interbeds. Unit 3 is this sort of stiff to hard clay, silty clays with shells. And then as you get into the alluvials below, it's sort of interbed silty clays without shells, and then just two little patches of areas of colluvial, which you can see here, the sands, the silty clays, the sands from Unit 4, and then the colluvial material down here. You can see the rock and sediment in between each other there. So it was quite important to distinguish that. And so these are the sort of the products that we went through with reference, the final product after all our work, to allow sort of this to go to tender and on to be constructed. So, and using the sediments to characterize the TBM. So we did do a paper in 2018 on selection of TBM for this, and these are some of the figures that I've carried forward into this. So looking at clogging factor based on the Atterbergs, and so you could see here the where it sits, and define what sort of material we got, but also the clogging factor, and we were satisfied with that. So the unit 4 and 5s were grouped due to their similarity, because they're sort of land-based. The Atterbergs for unit 3, generally dominantly medium to high plasticity, but based on the values assessed for the data units 3, 4, and 5, the potential for clogging, as I've just shown, and only a small part of the sediment in Unit 3 has a high clogging potential, and even less for Unit 4. So, so it's sort of, but they did, when they did tunnel through, they did encounter, clogging issues. So the brick pits that I showed you before, so this is sort of pulling out tunnels. So we sort of sat with the road. The tenderers did highlight that they believed that there was another tunnel in the area that connected two brick pits to another. And they did investigate that, but we did ask them to drill one more borehole, and that was where they think the tunnel was. And when they did that, they actually picked up the void. So that was a well worth effort to just to allay fears and allow this project to go ahead. So just the impact of harbour ground conditions to alignment design. So initially we looked at just an EBP TBM face, especially with the ground conditions we had under here with the fault, high water, water loss, with the packet tests and that. So that sort of discounted because we couldn't have the grades to get back up to without lengthening the tunnels over a longer distance, which would have put the cost up a lot more. We did look at the immersed tube, but as I showed you before, this is a major water crossing, and environmentally, the sediments do contain elements that are not favourable, and but also the channel here is a major flow for the environmental part of the harbour, and to block it would have impacts on other aspects of the harbour. So that was discounted. But also, as I showed you with the big ships, if we had to put cofferdams in here to actually do these immersed tubes, these connections, that would have impacted on the flow of the ships in the area. So we ended up adopting the pressurized TBM slurry, and that sort of went through that location that I showed you above. The other thing too is you can see from the early geophysics maps I showed you, this was the height of where the tunnel was, between the two publications here. But following our investigations with the geophysics, we did note that it was deeper, and following our boreholes, the inferred rock level is projected there. So it just shows the reliance of data, and these are lessons learned. And when we do projects, we do look at information, but we need to be sure of what we've got. And again, the impacts on the design. So you can see through here the alignment where it's gone through, and all the things that we had to adjust to get that alignment. We did have this sort of yeah, loose to dense sand material here that we were worried about, but the contractors were able to get through that and do a great job. So tunnelling uncertainty and types. The reference design assessed the shield tunnelling option for the harbour crossing, considering unstable ground conditions, both at the transition and in the central soft soil section. The transitions, because we're in a valley, the transitions are angled, and so understanding how those tunnels, these 7-metre TBMs, were going to go through and transition slowly without coming off a line was important. Hence why we tried to get the right orientation to the valleys. Handling mixed face conditions at the rock soil transitions was important. The lower cover of rock and lower cover to the seabed, especially close to the northern transition, which was this location here. We had really close, we tried to keep it one tunnel diameter below this area here. Yeah, so that was important too. And we had no investigation there because we had a lot of failed attempts, and the last attempt we had a ship, and following that, yeah, the cruise season come online and we couldn't drill there anymore. So difficult access from surface offshore if any ground improvement treatments are required. So this was done. We looked at grouting options, we looked at freezing options. So we brought in experts from overseas to assist in these things. The higher loads on the segmental lining in the soils compared to the rock lengths. So that was, yeah, there was a lot of calculations that went into assessing that based on the characterization and the data we had from the investigations. And also the cross passage positioning under the harbour, overwater drilling for cross passage 32, which was the southern was done, was that nice night investigation shot there where we had to confirm our where the rock head, because we lacked information there because the jack-up barges couldn't set up, and we had an opportunity to get this floating barge out there that could be anchored, and this was during the cruise liner season, and we're able to get this sonic drill rig down to Rockhead and confirm it. And we started at 10 o'clock at night, finished 5 o'clock in the morning, and pulled away, and the ship came in at 7 o'clock. So so it was a job well done. So tunnelling uncertainties and types. So we did have a risk matrix approach to this. So between slurry EPB, conventional slurry open, and hybrids. So you can see where we went with this. EPB, conventional slurry, sort of not an option, 3. The hybrid was a 2, and yeah, the slurry was just ended up being the 1. And so it's sort of, yeah, we had, just to note, the crown pressures were 4.2 bar in this location, and yeah, full face soil tunneling with high face support pressure. The reference design team decided on the slurry shield TBM. Management of the cutters during prolonged rock conditions and accelerated wear through mixed face condition requiring hyperbaric intervention in a few cases. The reference design established 1.5 diameter, that 11-metre cover with a minimum of 1 metre rock cover, covered to prevent blowout. Confirmation of rock cover above cross passages between running tunnels to enable their mined excavation. So these were done prior to opening up the segments. Yeah, they did do grouting and that sort of to eliminate any undue risk. potential need for ground treatment to mitigate geological risks, especially at the cross passages, and the successful tenderer at the end of the day did decide on the slurry shield TBM, as we noted there. So that was a positive for the client, but also us as reference designers. So during construction, there was a shaft on the northern side, just down from where we did those investigations for the dikes, and that was this deep shaft here, Blues Point shaft. So this was an extraction shaft. So the TBM first would come from Barangaroo, which was on the southern side. Here'd launch off and sort of came out here, and then it was there was a big gantry here that pulled it up, and it was taken across back to this location and dropped in again, and you can see here completed. But one morning we were, I think I was at the gym at the time, and got a phone call saying, oh, we've got bubbles on the harbour, and that was during the intervention. The TBM was parked and serviced, and the air tap was not turned off, and so when you get a whole lot of air, it seems to go upwards, and they had a nice fountain of air sort of projecting up here, but yeah, they stopped it and it all just died away. So there was no issues there at the end. So yeah, so the twin tunnels were successfully completed in March 2020, and so since then we've got the Western Harbour Tunnel, where there's a 16.7 metre TBM that's soon to be launched across that location I pointed out earlier, and that's to build a road tunnel connection as the harbour bridges. Yeah, this whole harbour bridge and the early IMT are quite congested at the moment. So yeah, so it's all happening. So the Sydney Harbour crossing was a key element of the Sydney Metro and City Southwest. Thus, the 160 metre length was the key to the success of the project. Early planning was needed to assess the locations where the TBM could be recovered and relaunched, as I showed before. You had the launch site on the south and the extraction site on the north. The complexity of these projects highlights the need for a stage approach to intrusive and geophysical surveys, from scoping right through to tender, so we can actually address issues as we go along. The importance of an integrated design team is important, as this combines everything together, responsibility of managing the ground investigation and the undertaking the design ensured that the adjusted alignment design drove the investigation requirements that we had planned. This was information, was critical to understanding constructability assessments and the ability of multidisciplinary team to undertake an in-depth study and analysis to confirm the feasibility of the safe construction, or basically testing the design of this short length of tunnel in a subaqueous soft ground condition. And you can see here, this is the cross passage under the harbour. Yeah, they dug it and it's quite dry. Yeah, we had two in the similar conditions on either side, and yeah, that was quite good to see. Quite good to see that. Thank you. I think that's everything.
Thank you, Dr. David. So the floor is open for the participants. Anyone has some doubts, questions? I had a list of questions. I had made some list, but your your precise summary had actually answered all the questions. I had around 7 to 8 questions.
If
Yeah.
you want to ask, yeah, just feel free. I'm happy to answer stuff.
No, your summary was quite precise. I just wanted to know a bit about your high logger this thing for ground you had used for ground investigations, right? To
Yeah, yep.
Yeah, yeah. Just can you
No,
just throw some light on it? Yeah,
yeah, no,
is it a software or is it something being developed by the university or
no, it's
what is
through
it?
it's an application used for mining, to actually define where they've got alteration, to allow sort of an understanding of what things, they can target for mining. And they're using it out at the core library, to the west of Sydney, to review a whole lot of core logs. But during the time, we had an opportunity, and we said, can we trial it and see how it works in a geotechnical application? So this is the first time we trialed it, but it was good in a way because it highlighted the mineral phases in the rock, if we had any, the weathering aspect of the rock, or the material, or the minerals that make up the sediments that we're going through. So it was an application, and if we have similar challenge in the future, it's something we could adopt again.
Yeah, and I had seen that I've observed that you had done a lot of series of tests like geological surface mapping, then geotechnical investigation, geophysical investigation, and a very detailed sort of geological sections have been formulated for this project. So
Mm.
apart from that, did you face any difficulties like any uncertainties or something from the
Oh,
geology point of view?
no, I think what we planned was what we had. There was areas where they didn't encounter groundwater, but that was corrected with pumping. Um, there was, we did initially in the reference design. We'd planned all the tunnels, and within weeks of handing over to tender, we did note that these dikes, especially the one at the earlier map, with an arrow sort of pointing to, there was an enlargement of the other tunnel that went through the area. And yeah, we had to move the alignment. Um, as you say, in the 11th hour, we had to move the alignment because it was too close for comfort to this enlargement. And the enlargement wasn't in any engineering reports. It was actually in a geotechnical um, log report, and sort of reading through it so I can just collate stuff. And I said to the design boss, I said, "Oh, I think we've got to change stuff." He said, "Why?" I said, "This is at the end of this report. Look." So it was quite things. So yeah, it was sort of, but we did, what we learnt on this. We carried forward on the next phase in the Western Metro West project, and so that was quite important, and that's successfully sort of moving along now. And yeah, they actually launched the slurry machines from the west of, the bays that they call it, through to the Hunter Street, which is in the CBD, where they're building the cavern at the moment. So yeah.
Yeah, and the picture, the image of the cross passage you had shown in the last slide, it was quite dry. So I think was it the type of luck or like you had actually predicted it that the cross passage construction would
Yeah,
be.
well, no, well, we said, look, if we can have it in this location. So we had to, yeah, there was a lot of discussion with fire, the fire brigade and all that, yeah, because the cross passage was longer than what should be. But yeah, what we did was we adopted a head of cover over that cross passage and the tunnel. And because we weren't sure we were going to be able to get in there and drill. Um, so we did undertake the drilling, at the request of the tenderers, and this was the only option, was to drill with a floating anchored barge, and we were able to get that done. And it proved that the rock head is where we said it was.
So the cross passages below the thing was actually greater in length as compared to the other cross passages. So did you face any difficulties getting the approvals and all because you're going off the standards and all, right?
Yeah, no, just in this one case, it was allowed because um, it was sort of noted. Yeah, if we had to go through the sediment, it would put people and the project at risk, and yeah, so it was sort of something, yeah, that we used, but it wasn't too far longer than what the normal spacings of 247. I don't know what the cross passage spacing that you adopt, but yeah, I think ours are 247 meters each, and so yeah, this one was just, I think, pushed to 40 meters more, um, but it wasn't a major issue.
Okay, so we have some questions from our audience.
Yep.
So Mr. Tai is asking about thank for the information. My question is regarding the tunneling phase of the project. Were there any problem ahead of tunneling as a TBM advances through the alignment just to verify the geological model, or the resilience was solely on the geological model only?
I think, yeah, with the um, in the sandstone, because it's a yeah, segmentally lined tunnel, and yeah, the I forgot to say that the TBMs on land were yeah, the double shield gripper type machines. So yeah, they were pushed along, and yeah, I think they just encountered one location where they had water ingress, but that was corrected with pumps. Um, but yeah, they went through the dikes. They had no issues. Yeah, the dikes, yeah, those major dikes that we targeted were up to 80, 90 MPa, and the TBMs just went through it, and they had no issues. So fault zones, yeah, there was no comments made about that. So it was something, we plan a lot of investigation, to target these major geological structures, and that's why we collect a lot of information, so we don't, um, yeah, just do geotech investigations for, yeah, just to fill a gap. Um, these are really targeted against major geological structure and that sort of stuff, or where we don't have any data um, to provide information to the designers and that. So yeah, that's where we target it. But no, there was yeah, I think one on the under the harbour they did, when they were, yeah, they were having experience issues with the slurry, and the muds clogging up. So they were able to adapt to that, and yeah, they went across and both sides, and yeah, successfully did it.
Thank you. So we have another question from Mr. Anshul Sindhavani. He's asking any advanced geological prediction system like BEM, TSP, or any other utilized during the TBM tunneling phase?
No, they just basically tunneled. Any investigations were carried out from the surface. So it's pretty. We don't have the complexities in geology that are experienced around the world. So it's the Hawkesbury sandstone basically has its UCS is probably around, on average, maybe 25, 21 to 25 MPa, with a maximum of maybe 60. The dikes, yeah, range from clays through to zonal areas up to 160 MPa. Um, yeah, the complexities are not there like they experience in, say, with the the areas in India or Europe or that. So it's sort of so yeah. So there's yeah, we don't really have that sort of requirement to investigate with the in the TBMs.
So yeah, I think the questions are done. So I just have one more question. It's irrespective of this topic. So we are now going towards the use of SFRC in TBM segments in two projects in India. We have adopted it. So
Yep.
what is the normal practice in Australia? Like, are you adopting the SFRC TBM segments or the
Oh
conventional two
yeah.
casting setup?
No, it's we're going down the path of dry tunnels. So segmental line with gaskets and yeah, it just provides a yeah yeah at the end of the day the operational expenditure will be less yeah, but yeah, the capital expenditure might be a bit higher, but yeah, over time the operation you get a tunnel that'll last a long time and won't impact on the the issues you have around metros with sort of services, electrification, tracks, and all that sort of thing. So it's sort of yeah, it's yeah, the segments are the way to go. Initially, when we went to yeah, there was pushback where they said we've got really competent rock. Let's just just tunnel it and use the competent rock. But the problem in the Hawkesbury sandstone is yeah, the groundwater transmit, but as it transmits out, we have ferruginous sludge that precipitates, and it just kills anything metallic, kills electrics. It really damages a lot of things. It fills up drains, so it's really um, it's not a good environment to be in. So hence, yeah, why even cable tunnels now are all segmentally lined.
Yeah, so I think this is it for the questions part. And yeah, we have Z. He's a newly
Hello.
elected ITA member, ITA young member.
Hello. Hello. No
So,
question.
any question?
Hello.
No, I guess he was just introducing himself. Yeah. So, yeah, thank you, Dr. David Roach, for your wonderful webinar on the Sydney metros. And I'm sure that your experience. Okay. So last question. Do you have some time, or we are just
Oh no, I'm happy. If you want to speak, feel free.
okay?
I'm happy to speak to everybody.
Okay, Mr. Vijay, you can, if you want, you can type or you can just switch on your
Feel
mic and camera and just
um,
ask him your question.
ask a question. Don't be shy.
I think he might be typing.
Which
Okay,
kind of segment joints are? Oh, I missed that one.
which kind of segment joints are treatment given with?
Yeah, I just maybe yeah, you might be able to. If you want to do, you could probably research about the segments that we did on the Sydney Metro sites. So you know, because that's yeah, I think they still adopt the same yeah segments with the um, yeah with the gaskets and yeah a lot of the dowels are prefabricated into the segments to allow what's this? Go ahead.
So yeah, you can just switch on your mic and ask him
Yeah, feel
yourself.
free to talk.
Hi, Dr. Roche. Hi, Mr.
Hello.
Roshi. Can you guys hear me?
Yeah.
Yeah, you're
Well,
Yeah.
audible.
I happen to be working in Western Harbour Tunnel, and you just mentioned that it's actually going to be mined by a large diameter of TBM. Now, given the fact that this is might be the largest TBM in the southern hemisphere, can you sorry?
It is.
Yeah. So can you?
Go. Sorry.
Yeah. I mean, in a nutshell, is there any issues related to large diameter TBMs, especially given the fact that it hasn't been done in Australia under the harbor? I mean, I know that Melbourne had experience of large diameter, but I think Sydney is now taking the lead in this matter.
It is because if you look from 1913 when we did the first tunnel, it wasn't until 1989 that they did an immersed tube, and then a bit later to now. So the Metro was a 7-meter diameter segmental line tunnel, twin tubes, as they do. We did look at single option large diameter, but the problem with that is connecting it back into the CBD was a challenge because of the deep basements we have in the CBD. So the twin 7-meter tunnels work a lot better in those sort of constraints. The Western Harbour Tunnel was initially designed for a immersed tube as well because they wanted the grades, but the contractors in their great ability were able to put forward the TBM option and highlight that they could construct this with the grades that were required. We did look at a tunnel TBM option in our early design days for that, but it was sort of required that they wanted to go down using this option. So yeah, I think in the future, larger tunnels might happen, but we just need to be aware that the constraints are because of the CBD and over in that location there, we're away from deep basements that may impact on tunnel alignments. So yeah, hence why they went with that. But it's only over a short area. It sort of just goes from just touch south of that Sydney Harbour to just a little bit north of where they are. So and then they'll end up burying the TBM. That's from what I hear. So yeah, the TBM's not going to continue as long as the TBMs we had on the metros.
Thank you very much,
that okay?
Yeah, thank you very much.
Are you based in Sydney or?
Yes, I am.
Oh, okay, we'd have to catch up.
Thank you. We will at some point.
Small world.
Yeah.
So what is the largest diameter TBM which is currently in Australia?
I think that's the one Mohammed just noted.
Okay.
Yeah,
I mean, Melbourne had 15.6.
Yeah, I think this is 16.7 or something from memory. Because I'm sitting as an SME on the verification for that. So it's interesting.
I think we are done with all the questions. And thank you very much, Dr. David Osh, for your wonderful presentation and giving up your afternoon to us, young members of India, and the other people as well. And I would like to inform all that the past webinars are also available on YouTube.